Hello everyone, my name is Vitalina Stepnikova and I'd like to introduce you to our project developed during the Erasmus Plus International Workshop in Ankara. The project is called Designing and Constructing a Solar Updraft Chimney with 3D Printing. I worked on this together with a great international team. In the next few minutes, I'll show you what we did, what challenges we faced and what we learned during the process. The first thing we did was research the topic. None of us had worked with solar chimneys before, so we started by trying to understand how they work both technically and environmentally. We looked at existing examples and different concepts to get a better idea of what solar chimney might look like and how we could possibly build one with limited time and materials. During this process, we found some interesting design elements. For example, narrowing the chimney can speed up the airflow, and inlet flaps might increase the intake by up to 55%. We also explored the idea of guiding the air through a gentle spiral structure with gaps to improve flow direction and stability. Based on all of this, we created our first sketch, combining these ideas into one design to see how they could work together in a practical prototype. The next step for us was to figure out what the actual dimensions and parameters of a solar chimney should be. By this point, we already had a clear understanding of its main components, the collector, the tower, and the turbine, and how they work together. So our goal was to understand what are the minimum sizes needed for each part to actually make the system work. We started comparing examples from real-life projects and simplified scientific models, trying to find a balance between theoretical efficiency and what we could realistically build during the workshop. After calculating the necessary parameters, we created our first 3D model of the solar chimney, but we still had doubts about how effective it would actually be. So we asked ourselves, how can we test the design without physically building it? We considered two options, either test its efficiency using a mathematical model or try to simulate both airflow and heating effects in a virtual environment. For the first option, we adapted an existing mathematical model from article. We adjusted it to fit our design, but unfortunately, the results showed almost no power output with our initial dimensions, which was a bit discouraging. Then we tried simulating the airflow in Unity. But as soon as we tested wind, it became clear that the results were far from realistic. The behavior didn't make physical sense, and adding a proper heating simulation would have required too much time and complexity. So we stopped there and decided not to continue down the simulation path. It wasn't worth the effort at this stage. Things really became dynamic once we all met in person. After reviewing our research and initial ideas, we split into two subgroups. One focused on building a physical prototype from basic materials to test the basic principle, and the other started working on 3D model for the final version based on the results. While testing the mockup, we also started optimizing the printable parts, trying to be as efficient as possible in terms of shape, material use, and assembly time. After many discussions, we agreed on a final version that would give us both the greenhouse effect and optimal airflow. For the turbine, we decided to use a thin metal sheet fan instead of a 3D printed one, as it was lighter and more effective. Once printing began, we started assembling and sealing the modules carefully to ensure airtight connections. The fan was placed inside the collector with an airflow cone beneath it. We used a plexiglass surface to allow sunlight in, heat the air, and trap it inside. In the end, we were even able to produce a small amount of voltage, which felt like a small but real success. Overall, the journey was intense, well-structured, and truly rewarding. We faced only a few technical issues, like parts of our 3D geometry being too thin for printing, or the fan being too heavy, which forced us to change our plan, but nothing stopped the process. Looking back, we've learned that building a working solar chimney requires precise calculation, careful design, and lots of trial and error. We also realized how important it is to plan the production timeline realistically, especially when dealing with 3D printing and physical assembly. If we had the chance to do this again, we would probably start testing and adjusting much earlier, but overall it was a great experience with valuable lessons. Thank you for your attention.